Fonseca-Lopez, and this is Lab 4 Oscillations for Physics 2211. So just a small overview of my presentation, give a short introduction to the lab, talk about some of the fundamental concepts we applied throughout it, give a demonstration of my tracker analysis from the provided video, show the computational model and its code, make a comparison between the data of the two, and answer some additional questions at the end. So the purpose of this lab was to investigate the motion of a spring mass system with a mass oscillating on a spring or swinging arcs. The tools I used during this lab were Tracker to analyze the video with the spring mass system, GlowScript to construct a computational model of the system, and Microsoft Excel to plot the data and insert it into the GlowScript model. The results for this lab show my predicted and observational models were similar, considering they shared the same initial conditions. I also observed that the total change in energy was zero, lining up with the energy principle. Some fundamental concepts of physics applied are Newton's second law, which we use to derive the position and velocity formulas that we applied in the computational model. We also have energy principle, which in our case will transfer the work done from the surroundings into our potential energies. So our total change in potential and energy will be zero, and our potential energies will be the kinetic energy, the spring energy, and the gravitational energy. So now our system consists of the spring, mass, and the Earth, while we have nothing in our surroundings. Small portion of the tracker analysis, we have the mass of the object, which is 0.402 kilograms, the length of the spring that we'll use for our comparison, which is 0.7 meters, and the initial position and initial velocity from our object. So here's just the code from the computational model, where we set the initial conditions, calculate the spring constant and the relaxed length of the spring, and then on the right we make calculations for the gravitational force, the spring force on the mass by the spring, the net force itself. Then we apply the momentum principle to the ball. Then we update the positions of the spring, and then we calculate the change into energy for our potential energies. So here's a comparison of the data. As you can see, our model seems to go a little further in both the x and y coordinates, but they do follow a very similar trend. Some additional questions. Possible errors throughout the experiment. There could have been mistakes in setting the initial conditions for the computational model, which threw it off, and that could have been what caused it to go so much further in both the x and y coordinates from the model itself. And then there could have been differences in the surroundings. The computational model accounts for no effect on the surroundings, but in the video itself, it could have been experiencing air resistance. There also could have been an incorrect calculation for the spring force constant, and as well as the relaxed length of the spring. Was the energy principle satisfied in this case? Yes, in this case, the energy principle is satisfied, as the change in total energy remains zero throughout the oscillations of the spring system. And since there is no work being done by the surroundings, the energy is moving between the potential energies, meaning the total energy will never change. So estimates of oscillation periods. Using the data from Tracker, we can estimate oscillation periods for the x and y coordinates. We needed to do this to find the spring force constant, and in my experiment, I used the oscillation period from the x coordinate, which was t equals 1.71 seconds. But it's not too different from the oscillation period for the y coordinate, which is t equals 1.63 seconds. So in the end, I don't think there would have been too great of a difference, but if we used either the oscillation period from the x coordinate or the y coordinate. Thank you for listening to my presentation.